Jack Jackson. In this video, we're going to derive the derivative formulas for cotangent, secant, and cosecant. Now recall that we've already found that the derivative of sine of x equals cosine of x, the derivative of cosine of x equals the opposite of sine of x, and the derivative of tangent of x equals secant square of x. Now with that in mind, and the fact that we can rewrite all of the remaining functions as reciprocals of one of the functions we already know the derivatives of, we can use that along with the substitution, the chain rule, and a couple basic identities, and we'll be able to knock out the derivatives of these very quickly, and pretty much all in the basically the same manner. So for example, the derivative of secant of x. Well, secant of x is cosine to the negative 1 power. Now this is not inverse cosine of x, this is 1 over cosine of x. This is truly a power, which we need to write it out here for it to be a power. Now the derivative of cosine of the negative 1 is the derivative of u to the negative 1, where u equals cosine of x. Well, according to our power rule, that's negative 1 times u to the, subtract 1 from the power, negative 2. We did a substitution though, so that's times the derivative of the u. The derivative of u is the derivative of cosine of x, which is minus sine of x. U is cosine of x, so we have minus 1 over cosine square of x times minus sine x. Now first of all, the two negatives cancel, so that makes positive. And I'm going to think of the sine of x as being over one of the cosine of x's, and that still leaves us a 1 over cosine x. We can rewrite 1 over cosine x as secant x, and we can rewrite sine of x over cosine x as tangent x. So the derivative of secant of x is secant of x times tangent of x. Okay, here we see the results here. So secant of x is our original function, which is in blue. And notice that it has its derivative, which is secant of x times tangent of x, is in red. So notice again some characteristics of this. Everywhere the original function is at a minimum, which occurs up here, a local minimum at, for example, at 0, 1, at 2 pi 1, at 4 pi 1, at even multiples of pi for x and y is 1. Those are local minima. Everywhere that happens, the derivative is going to touch the x-axis or cross through the x-axis. Everywhere we have a local maximum, that's going to occur at odd multiples of pi for x, and of course y is negative 1. Everywhere we have those, we also have the derivative is 0. So the derivative actually crosses the x-axis at every multiple of pi. Now, as we look at this a little bit more closely, we see that, for example, between 0 and pi over 2, the graph of the original function is increasing from 0, horizontal tangent, from a horizontal tangent line. And then the original function increases there, and the slopes are also increasing. So we see that the derivative is going to be positive and increasing there. As you look on this next piece, we see, say from pi over 2 to pi, we see that the original function is increasing, so the derivative is still positive, but the function is concave down, so the derivative is decreasing. So for example, this whole piece, the function is concave down, so its derivative is decreasing. Whereas this piece right here, say between negative pi over 2 and pi over 2, the original function is all concave up, so the derivative function is increasing. Okay, so you can see some of those basic things. Also notice that where the original function has a vertical tangent line, so does the derivative. Similarly, we can do the other two functions. The derivative of cosine of x, cosecant of x, excuse me, is the derivative of sine x to the negative 1 power. Now, the sine of x to the negative 1 power is u to the negative 1, and we want to take the derivative of that, where u equals sine of x. So it's the power rule, so it's negative 1 u to the negative 2 times the derivative of the u. U equals sine of x, so substitute that back in. The derivative of sine x is cosine x. U to the negative 2 is 1 over u squared, so we get minus 1 over sine squared times cosine of x. In a similar manner to the last one, we split the sine of x up putting cosine x over sine x, which becomes cotangent of x. That leaves 1 over sine of x, which is cosecant of x. And I have it in the final answer, but it looks like I dropped a negative at one point. So there's a negative there, and this needs to be here, and it's there in the final answer where it should be. Okay, and so the final answer is the derivative of cosecant of x is minus cosecant cotangent. Cosecant of x, cotangent of x. And if we graph those together, you see this picture here, similar to the last picture. And I'll let you look at those and see the graph characteristics. For example, everywhere there's a minimum here or a maximum on the original function, we have the derivative is crossing the x-axis. The derivative is the one in red. The original function is the one in blue. Notice everywhere the original function is concave up, the derivative is increasing. Everywhere the original function is concave down, the derivative is decreasing. Where the original function is increasing, the derivative is positive here and here, and the derivative is negative in here where the original function is decreasing, and so forth. Now, how about the derivative of cotangent? Well, cotangent is a reciprocal of tangent, so the derivative of cotangent of x is the derivative of tangent of x to the negative 1 power. Again, make a substitution, u equals tangent of x, and once again, for the third time in a row, we're taking the derivative of u to the negative 1. So that's negative u to the negative 2 times derivative of u, just like before. So this is minus 1 over u squared. But this time, the u is tangent of x, the derivative of tangent x is secant squared. So let's write everything in terms of sines and cosines and then see what we can do with that. Tangent is of x is sine over cosine, so 1 over tangent of x would be cosine over sine, but it's squared, so it would be a cosine square in the numerator, and you got a sine square in the denominator. Secant square is 1 over cosine square, so these two cosine square of x cancel, and you get minus 1 over sine square of x, which is minus 1 over sine. It's 1 over sine squared, and then the opposite of that. So in other words, it's the opposite of cosecant square of x. Once again, we can look at the graphs. The blue is the cotangent function, and the opposite of cosecant square is the red one, which is its derivative. Notice that where the original function hits the x-axis at odd multiples of pi over 2, then in fact the derivative is at a maximum because that's an inflection point also of the original one. Anywhere we notice that the derivatives are the original function is decreasing on any one particular piece. Anywhere it's defined in an interval around that, it's going to be decreasing. So in fact, the derivative is always a negative value, negative output, which is what we see here. The derivative is decreasing on each piece. The original function is decreasing on each piece, so the derivative is negative everywhere. We do have a change in concavity everywhere we have an x-intercept, so it's also an inflection point, and those are going to be maxima, global and local maxima actually, for its derivative. Okay, so let's summarize. What have we proved so far? So notice that we have these basic derivatives. We've got the derivative of sine x is cosine x, derivative of tangent of x is secant square of x, and derivative of secant of x is secant of x times tangent of x. Now, look at the ones that start with the sine, tangent, and secant. All end up having a +1 coefficient in the derivative answer. But notice all the ones that start with cosine, cotangent, cosecant, all start with the -1, and then you're replaced by the cofunction here. So you replace sine by cosine, then in the problem you replace cosine by its cofunction, sine of x. But the ones that start with have a minus in front. Derivative of tangent is secant square, so cotangent derivative would be cosecant square, but it starts with a minus. Derivative of secant is secant of x times tangent of x. The derivative of its cofunction, derivative of cosecant, would be cosecant of x times cotangent of x, and then you have a minus 1 in front. So the ones that start with co have a minus in front, and the ones that don't start with co have positive in front. So you need to memorize these 6 basic derivative rules, but if you can just memorize the ones on the left and memorize how to get the ones on the right, you can get those pretty quickly with the little rule that we've looked at. So in the next video, we're going to go along and practice using these 6 derivative rules, along with some of our earlier rules as well, to put them into use.